Hi, I'm Jenny, and this is my video experiment report for experiment 4. So introduction. The purpose of the experiment is to collect observational data of magnet falling through a conductive tube of aluminum foil, model the magnet or tube interaction computationally, and finally compare computational prediction with the observation. The main result of the experiment is 1. The measured average time it takes for the magnet to fall is 1.1 seconds, and 2. The computational time of magnet in the tube is 1.384 seconds. So here's some initial conditions and assumptions. So in this experiment, we are basically measuring and calculating the time of the magnet falling through the aluminum foil. So the initial conditions include the length of the tube, the inner radius of the tube, the mass of the magnet, and also the magnetic dipole moment of the magnet. So the assumption we made is that the air resistance is negligible. And in this experiment, the system is bar magnet while the surrounding is the row of aluminum foil and the earth. So the main physics idea is composed of 3 theorems and equations. So the first one is Faraday's law. It's a quantitative relationship expressing that a changing magnetic field induces a voltage in a circuit, which induces another magnetic field. We also have Boyd-Savitt law. So this is a general equation for magnetic field. And finally, you have the equation for magnetic force, F equals to I times delta L cross B. So with these 3 equations and theorems, we can get the equation of force on wire loop. F equals to I times the parameter of the loop times B field times sine theta. So for the first part of the experiment, I manually measured the time of the bar magnet falling through the row of aluminum foil with my smartphone. So there are a total of 5 trials, and the average time measured for these 5 trials is 1.1 seconds. And then we come to the computational model. So there are in total 8 steps of our computational model. So the first one is, in the first step, we define some initial conditions of the experiment like mass and magnetic dipole moment. And in the second step, we calculate the magnetic field, and with the magnetic field, in third step, we calculate the derivative of flux. So with the derivative of flux, we can get the current, which is calculated in step 4. So with the current and B field, we can calculate the magnetic force on ring and also the magnetic force on the magnet, which is step 5 and 6. So then we add the value of gravitational force and magnetic force. This is the net force, which is step 7. And in step 8, we use net force to calculate the velocity of the bar and also the position of the bar magnet. So here's the result of the computational model. So the computational time in tube is 1.384 seconds. So it's a bit different from the measured time in tube. So there is some possible sources of error. So bias may happen when I'm measuring the falling time, the tube length, and magnet mass. And there might also be bias of calculated magnetic dipole moment from lab tube. So what if and why? What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So if the resistivity of the conductor were reduced as close as possible to 0, the value of the current would reach infinity, which leads to a huge upward magnetic force that also reaches infinity. What if holes or slots were cut into the tube? How would this affect the ring current in your model? So the induced current would decrease because the flowing of the current would be impeded by the holes and slots. Okay, that's all.